Of this experiment is to study and verify the truth tables of half adder, full adder, half subtractor, and full subtractor using logic gates. Objectives. The objectives of this experiment are to understand how binary addition and subtraction work at the logic gate level, to design half adder and full adder circuits using AND, OR, and XOR gates, to design half subtractor and full subtractor circuits using NOT, AND, and XOR gates, to verify the truth tables of each circuit using a digital logic trainer kit, and finally to learn how these circuits are used in arithmetic logic units inside digital systems. Apparatus required. The apparatus used in this experiment is a digital logic trainer kit. This kit includes basic logic gates like AND, OR, NOT, and XOR, input switches to provide binary values, LEDs to display the output, and jumper wires to make the required connections. Full subtractor. Finally, let's look at the full subtractor. A full subtractor takes three inputs, A, B, and bin, the borrow in. It gives two outputs, the difference and the borrow out. The logic equations are difference equals A exclusive or B exclusive or B and borrow equals not A and B or B and B in or not A and B in for the full subtractor. Truth table. When A is 0, B is 0, and bin is 0, the difference is 0 and borrow is 0. When A is 0, 0, B is 0, and bin is 1, the difference is 1 and borrow is 1. When A is 0, 0, B is 1, and bin is 0, the difference is 1 and borrow is 1. When A is 1, 0, B is 1, and bin is 1, the difference is 0 and borrow is 1. When A is 1, 1, B is 0, and bin is 0, the difference is 1 and borrow is 0. When A is 0, 1, B is 0, and bin is 1, the difference is 0 and borrow is 0. When A is 0, 1, B is 1, and bin is 0, the difference is 0 and borrow is 0. When A is 1, 1, B is 1, and bin is 1, the difference is 1 and borrow is 1. In simple terms, the difference is 1, 1 when there is an odd number of ones between A, B, and bin. The borrow is 1 when B is greater than A or bin is required to subtract.
For full subtractor, we have used three inputs A, B, and B in, which is borrow input. To get difference as a output, we have performed A XOR B, and the output of it is again XORed with B in, and the final output generated is connected to the LED representing difference. For borrow output, we have created input A bar using NOT gate and then replicated it two times. We have also replicated our input B and B in. Next, we have performed AND operation on A bar and B in, A bar B and B B in. The output of A bar and B in and A bar B is used as input to perform AND operation with output of B B in. The final output is connected to LED representing borrow out. For full subtractor output, we have 8 combinations. When all the inputs are 0, difference is 0 and borrow out is 0, that is no LEDs glow. When A and B are 0 but B in is 1, difference is 1 and borrow out is 1, therefore both LEDs glow. When A is 0, B is 1 and B in is 0, difference is 1 and borrow out is 1, therefore again both LEDs glow. When A is 0, B is 1 and B in is also 1, difference is 0 and borrow out is 1, only the borrow LED glows. When A is 1, B is 0 and B in is 0, difference is 1 and borrow out is 0, therefore only the different LED glow. When A is 1, B is 0 and B in is 1, difference is 0 and borrow out is 0, therefore no LEDs glow. When A is 1, B is 1 and B in is 0, difference is 0 and borrow out is 0, therefore again no LEDs glow. Finally, when all the inputs are 1, difference is 1 and borrow out is 1, therefore both LEDs glow.
Conclusion. To summarize, half adders and full adders are used for binary addition. Half subtractors and full subtractors are used for binary subtraction. These circuits can be built using basic logic gates and tested using a digital trainer kit. Understanding these circuits is essential for learning how computers perform arithmetic operations at the hardware level.